Alright, this is going to be episode 21 in the video series going from a noob to a veteran ASM coder. Alright guys, after this we only have 2 more episodes left in your long journey. So for today's episode we got about creating stack frames. This is going to be a tutorial over how to create custom stack frames to suit your needs in a complex code instead of using the generic stack frames we used in the past, aka the push/pop the stack method. Okay, so you may have seen stack frames we made in the past, something like this, push the stack, back up 14 through 31, load it back up, pop the stack, or you might see it something like this. And like when we did the episode on function calls before. So these work and whatnot, but if you're really trying to follow the right etiquette for coding, just assembly in general, not just MKW, and also optimization, you only want to back up the registers that you're going to use. So if you're backing up 14 through 31 and you're only using like 30 and 31, it seems kind of silly, right? Now, obviously, for function call cases, there's really no way getting around it. You're going to have to store everything. But if you're in a case where you're not doing really function calls or something like that, or maybe you are doing a function call or something and you don't need to back up all the registers in some weird scenario, I can't really think of one right now, but this will teach you how to create custom stack frames just suiting your needs and how many registers you need. Okay, the purpose is it's universal. You can use this in any Wii game, it works. There's nothing here that's like MKW specific in any way, shape, or form, so that's a good thing. This is why we would use it. The second thing too is that you can store stuff to the stack frame instead of maybe storing stuff to the exception vector or using a function call to create allocated memory. This would save you a lot of space, or it would shorten your compiled code length quite a bit instead of using all the stuff I just mentioned. Stack frames could be easier for your particular situation. Okay, so we need to go over how do stack frames actually work and what do they look like. So we'll just cover the plain Jane push/pop the stack method. Okay, so let's go ahead and boot the game. Let me just make sure I got no codes on right here. We'll get it to a point and we'll pause it. Okay, so this will work. Okay, so if we go ahead and look at the registers, now keep in mind Dolphin likes to use SP for this register. What is this? Well, it's a pointer. Alright, so let's go ahead and look at it in Dolphin Memory Engine, aka the live RAM viewer. This is what we're pointing to. Okay, so the stack pointer, it's a memory address pointer to various values that get backed up during various subroutines, and certain things might be backed up for a certain amount of time or stayed there for a certain length or retrieved later. Basically, the storage on the stack frame occurs in layers for a function call. We have like 5 function calls. You have the top function call that will initially store a layer of information. Then the next one will store even more on top of the current stack frame, make a new one, store it on top. The third one will make another stack frame on top of the previous stack frame, and keep building until you got layers of data that it can retrieve back later. So this is how stack frames generally work. So what this does is it stores the pointer, it stores R1's value, okay, behind where R1 is at, okay, if that makes any sense. So what this does is, because the stack frame is a pointer, you can create one by taking the old value and storing it somewhere earlier in memory. And depending how much earlier, depends on how much data you want to back up. So the further back you store R1's old value to a new spot in accordance and reference to R1's value, the more data you can store, the bigger the stack frame is. So the more larger this negative number, the bigger the stack frame is, okay? The further back you take R1's value and store it behind what is R1, the larger stack frame you create, and then you can store your stuff accordingly based on how much of a stack frame you create. Okay, so let's go ahead and do some raw ASM compiling so we get an idea. Let's go ahead, put some stuff here. Okay, so we can go ahead and do this, copy. Well, let's go ahead and post this all. So we'll show you step by step what this conventional stack push does, push and slash pop the stack. Get these plugged in. Notice how Dolphin uses the term SP for R1. Okay, there we go. And just to keep FYI, Dolphin converts values a little weird when it demonstrates them. 50 in hex is the same as 80 in decimal. That's why I have negative 50 in hex and positive 80 in decimal. So anyway, going back to that, take a look. R14's value and like R15. I know we have some data here. We just need to plug in. So values 14 through 31 will be put on our newly created stack frame. So right now we're on whatever current stack frame we're on. Doesn't really matter. So we need to create a new one no matter what, because we're adding more data to the stack frame. You don't want to add it on the current stack frame because you'll obviously just break the game. Okay, so now check this out. Here's the current stack frame. It's pointing right here in memory. So stack frames grow. Let's see, they grow down, if that makes sense, or they grow, a better term is stack frames grow towards lower addresses. They don't grow down like when you're scrolling down through a live RAM viewer. They scroll up through smaller memory addresses. So when we store this new stack frame, like we take R1's old value and store it in reference to its current value, it goes up. So look right here. Now 50 in hex is 1, 2, 3, 4, 5. So it's going to store the value right here. Now check out when we step in Dolphin. Now we're going to execute the first instruction. Doesn't really matter what we're talking about. Now look what happens. Remember, R1's current value is 802DA118. Boom. Look, it gets stored 50 in hex before 2DA118, the value right here. See that? This value right here gets stored right here. So this is R1's old value. We thus created a stack frame. So we know that this data right here is safe to use. Now, because stack frames grow towards lower memory addresses, whenever we're talking about lower memory addresses in reference to our stack frame, it's called negative stack space. Negative means decreasing. So notice how we stored. So if, let's say right before we made the stack frame, remember this is the old stack frame right here, highlighted in blue. Everything above is negative stack space. So thus we went towards the lower memory address, created the stack frame. Now watch this data all right here. Watch what happens to it. Gets replaced with the data from 14 through 31. And now just to show it works, let me just put null here. Now remember we had all F's in 14. And then we had all A's in 31, so let's say we used a code where we used 14 and 31. Remember, it's stored on the stack, alright? Universal, works for any Wii game. We load up, boom, look, 1431 get replaced. Now watch what happens to register 1 in the registers tab, okay? Boom, we put back the old stack value. And it doesn't matter if we leave data here, because this is negative stack space. So when a new stack frame gets created, it's going to get wiped anyway. So this is how push/pop the stack method is safe to use. I explained in the old episode it's 99.9% safe because you make a stack frame too big, depending on the scenario where the stack frame's at, currently in Mem80, it could cause a crash. And obviously stack frames are always in Mem80, just an FYI. Even though it does act sort of like dynamic memory, it's just the rules of Broadway. Stack frames are in Mem80. Okay, so that is how stack frames work. Obviously, if we're talking about the stack frame for function calls, like R3, you create accordingly. So how do we calculate the amount of stack space we need? Well, there's some rules. Obviously, you guys know each register takes 4 bytes in memory, a word in memory. Okay, so we went through over the illustration. I put a little text edit illustration. Okay, stack frame rule size limits. There's one thing you should know. As you can see, blah 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 blah. There's a padding situation with stack frames. Whenever, let's say you calculate the size. Let's see. Let's go back here. New R1. Okay, so one thing I forgot to mention is, notice how our new stack frame is right here. Notice this padding is zeros. Now you notice how when I did store multiple word, load multiple word on push/pop, the stack method, we didn't use an offset of 4, we used an offset of 8. The reason is, excuse me, we have this padding here, is just in case you use a code that has a function call, the function call will store the current link register value right here. Broadway is designed, the way PowerPC is designed to whenever stack frames are created, a new stack frame is created, the current link register is put on the older stack frame, if you will, in this padding. It's just a rule of Broadway. It's a rule of most PowerPC chips. They all follow this rule. So to have proper etiquette, we follow this rule too. And also as a just in case thing, if you have any function calls in your code. Even you could probably get away without doing this if your code didn't have function calls, but it's better just do a force of habit, and you get so used to it, you just do it every time, and you don't even have to think about whether or not your code has a function call. Okay, so stack frame, size, rules, and limits. Okay, so this is the formula we use, very simple math. This 8 is required because you have the padding of the word value for the storing R1's old value, because R1 is a word in length. Then you have the extra 4 of padding right here, so a word plus a word is a double word, which is 8 bytes, which is why we have the 8 here. So this is a simple formula. You're going to take the number of registers you're backing up. Now keep in mind, this is for the store multiple word method. So when you want 2 registers, they have to be R30 and 31. If you want like 4 registers, they have to be R28, 29, 30, 31. I could show you a technique where you don't have to do this, but I don't think I've ever been in a situation where I needed that technique. But anyway, we're doing what's called store multiple word, load multiple word method, and we're working with just the general purpose registers. So let's say we want these 4 registers to use. You have assembly code. You used up like 10, 11, and 12 on the registers, and some other register like in the default instruction. You need 4 extra registers. Instead of push/pop the stack to use 14 through 31, we just need to use these guys right here. So what we can do is just do 4 times the number of registers, okay, is 16. 16 plus 8 is 16 plus 8 equals 24. Now we're going to convert that to hex. Which is 18. So you're probably thinking we could do something like this. And we do the loading and adding stuff accordingly, but we just need to worry about pushing it, obviously. You guys already know this is, well, just in case you don't know, this is the opposite. You guys know about the generic stack frames we covered before. It would just be like that. So you're probably thinking, okay, we're good, right? Actually, no, we're not. And the reason is, once again, PowerPC chips, including Broadway, have more specific rules on stack frames. Every Wii game follows this, obviously. Stack frames must be quad word aligned, meaning this value right here must be divisible by 10 in hex, meaning this value must be ending in 0. So when you're making this stack frame, the last digit has to be in 0. Now what happens if it's not? You have to bump it up. So the next closest divisible hex number that's divided by 10 in hex after 18 is 20. So this would be the correct way to push and push / pop the stack for 4 registers using the multiple word method. Give you some time to digest that information. Okay, so let's go back to the thread. You understand that. Overview, we talked about recovering. I already went over that in the visual display of why we have these load instructions and the add instruction. Okay, using store, load immediate. This one's kind of weird. Let's see, blah, 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 blah. Okay, let's say you want registers for whatever reason. I don't know why you would ever need to do this. In fact, I might delete this chapter from the tutorial, but we'll go ahead and cover it just in case. Let's say you want to back up R17 through R19. You're going to do the formula. 3 times 4 is 12. 12 plus 8 is 20. 20 in hex is 14. Bump it up. We need a stack frame of this size. So we're going to do the first instruction like usual. Okay, like that. Now, I'm not going to cover exactly how to do the store string word immediate and load string word immediate. Those examples are in the ASM reference page. It's a thread. If you haven't really looked at it much, which I don't see why you wouldn't in your assembly journey, it's under the resources and references subforum under hacking. So just go there for our little simplified ASM reference page. So essentially, this would be the technique to do it, and let me explain how this instruction works. Okay, so first, actually we got one more instruction. Okay, so essentially, remember that padding I told you about, the padding of 8 we needed? Okay, so we have to add this padding and we put it into a temporary GPR, okay? And 12, this 12 here is for 12 bytes. Remember, each register takes 4 bytes. A word apiece, 3 words is 12. So this is why we use this 12. So let's go ahead and just demonstrate how this would work. Just if this is a little confusing, but I don't see why you would ever need this. Let's go ahead and do this. Go like that. We'll go to the code view. It's been a while since I've done this string word immediate, so this will be a little refresher too. We'll just replace this. Okay, so let's go ahead. We're gonna put some custom values here for 17 through 19. And we'll bring up Dolphin Memory Engine. So let's go over exactly what would happen. So first we create our stack frame, okay? And as you can see, it gets stored right here. This is where the old stack frame pointer is. We store it right here, okay? Now remember that padding I told you about? The reason why we add 8, alright, to the stack pointer and put it into this temporary GPR is that, remember, we're right here. The first value has to get stored an offset of right here. This is why we're adding 8 to the stack pointer and putting the result into a GPR. Obviously, because of register safety, you would use something like 11 and 12. So keep in mind, if for some odd reason you have to do this string word, load string word method because you didn't want to use the multiple word method, you're going to have to use a GPR. Like I said, I might remove this chapter from the thread because I can't even think of a situation why would you use this. But anyway, nonetheless, let's go. And as you can see, 2DA100 and R11 points right here. Now what the string, store the string word immediate is, it's going to start at 17. Notice how 17 is the destination register. Alright? And it's going to do 12 bytes, 17 through 19. And it uses R11 to store it in reference to. So it starts storing it at this address right here. So watch what happens. from right here, these 3 words right there, and boom, there you go. So, and then you just reverse it. So we'll go ahead and reverse it for the string word. So this is how you would reverse it. And let's say this is at the end of your code. You would go like this. Okay, you would make sure R11 is that value of the stack frame you're currently on. If you didn't modify R11 or whatever register you're using for this instruction wasn't modified, you won't need to do this again. And then you just do the opposite of store string word immediate, load string word immediate. Just the exact opposite. You just switch the operands per se, just the instruction names themselves. Leave everything the same or whatever. Gotta fix that little typo. I put R12 there. I'll fix that in the thread. So we can go ahead and plug these instructions in just to show you if you want to see even further. Load string word immediate, replace. Okay, so what we're going to do is I'm going to put some random junk in here just to show that these registers are being retrieved and recovered. And remember, R11 has to be the value that we used earlier. So if you modified this, all you do is just add 8 to your stack frame, and it'll put it back to where it was. Okay, so let's go to memory. We're retrieving these 1s, the 2s, and the 3s. They'll be put in 17 through 19. Here we go. Boom, they get replaced. Fix the stack pointer, and the stack pointer is back to its old value. So that did take a while, but that's how you use the string word method. And I am actually going to go ahead and fix that little deal while we're already on here, just so no one gets confused by that. Okay, now going back down, storing floats to the stack frame. Okay, so let's just go over this method. Let's say you're storing 6 registers. You're using the store multiple word, load multiple word. So obviously this is going to be R26 through R31. That's 6 GPRs. But in the process, you need to store these 2 floats. Now the calculation is pretty similar, but when we store floats, we always back them up first in double precision or whatever. So because of that, each floating point is a double word that we're storing. So the calculation is going to be a little different. First, you do 4 times 6 for the GPRs. That's a decimal number of 24. Okay, and then we have 2 floating points. 2 times 8. All right, 2 floating points. That's 16. You add that together, we have 40. Now remember that special 8 number we always have to add for accounting the padding for the word is zeros for the padding and where the old stack pointer goes. That equals 48 or 30 in hex. And we see our hex number is already divisible by 10, or it ends in 0 digit, so we don't need to change it at all. So thus, if we wanted to do the stack frame for this, I'm just using R1. If you want to use SP, it's just whatever you're feeling. Now, what do you store first, the floats or the GPRs? It doesn't matter. It's whatever you want to do. Just do what's easier for you. I personally like to use the stuff. If I'm having GPRs and floats, chances are I'm backing up less data on the amount of floats than the GPRs. So I'd store the lesser amount of data first before I store the other portion that's more. Now, there's one kicker about floats, that you have to store them once at a time. So keep that in mind. If you really need to use floats and you have to push a stack, this is going to waste a lot of lines in compiled code length. And then once you get done with that, remember, now obviously we have the 8 for the initial offset. 8 plus 8 in hex is 10, which is why it goes here. Now remember, floating points take 2 words, so 10 plus 8 in hex is 18. And then we don't need to worry about anything else because all the GPRs get stored after that. And then if you're going to load these, you just do it in reverse. And obviously, if you want to use SP instead of R1 like that, it doesn't matter. All compilers know about this little nickname for the stack pointer. Okay, and that's really about it. The only we covered illustration, a visual representation of stack frames. We talked about the rules, the alignment issues, why we do the padding of 8. We talked about floats, string word, and load string word, which I still don't see a reason why you would ever use it, but somehow just in case you have it. And now, quick handy note about the stack pointer. Remember I told you about the negative stack space is like safe to use to safe to overwrite? So if you have a code and for some reason you got to store data, but it's a situation where you can't store it to exception vector area, or you don't want to, and you don't want to call a function allocate memory, you could just do something like this. Like, I don't know, like that. So anything negative is safe to use. So -4, -8, -C, it doesn't matter. So you store in one register, you can store it right before, -4. And I'll just leave it decimal just for the heck of it because I can't type today. But obviously this has to be negative, so sorry if I kept typing that. So this has to be negative, and what this will do is wherever the stack frame is, it stores above it or in lower memory address. Technically, this isn't proper etiquette for assembly programming in general. You're kind of not supposed to do this. But in MKWe, we can bend the rules a bit. So I had to do this, I think, for a code. I think dealing with converting integers to a floating point or something like that. And I had to use this for whatever reason. I think I had to use it, don't remember. But I had tested in codes. It does work. It doesn't crash. It could crash just because it depends on where the stack frame is at the time and what the game is calling. But if you are in a situation where you need to use negative stack space, you can try it out and see if it works for your code. But as mentioned before, it's technically not proper safety etiquette. Okay, and that is it for about creating custom stack frames. Alright, in the next episode, we'll talk about using macros for your compilers. Alright, thanks for watching.